using quite a lot within R. But basically, what we want to do is show more or less what we are using in a day-by-day basis to evaluate some scheduler features.
My laptop stole the screen. So
yeah. Or you can just disconnect your.
Oh yeah.
Okay, it's still there. Let me see how I can put this through. The director is setting up the stage. Let's wait. Should I try to? It was working with this one.
Can you use this?
Yeah. You can use your.
Yeah.
It's not there. We're just going to run this share. Yep. And then go to view present. Yes. Yes. Cool. Okay, so so this tool is called LISA, which stands for Linux Integrated System Analysis. So the idea is to just describe a little bit what is this tool. I will show some examples of plots and analysis that we can generate, and then I will Brendan will do some kind of live hands-on session showing some similar features that we can use. So what is this? It's basically a toolkit, is a framework, is a collection of libraries. And the goal for this library was to try to support the study of existing kernel behavior. Like, for example, one of the really first things that we started working with was, okay, PELT, we have this signal within the scheduler that tracks the utilization of tasks. We want to understand how it works, and even more importantly, we want to understand how it changes if we tune some parameters, how we can risk to break it if we introduce some patches in the kernel, and so on. And so the idea is also to analyze future works. So try to understand when we produce some patches, how we affect existing behaviors, and possibly try to have a little bit of regression analysis. So if there are specific features that are tracked by some test, we want to be able to pinpoint exactly which features has been broken by a certain modification that we have done with certain patches. So have a clear indication where we have to look in the code for fixing the issue. And another issue that we found when we started working is that everybody is using its own set of script, which is perfectly normal and fine. Everybody's comfortable with their own tools. But when it comes to share results in such a way that someone can reproduce the results to the other end, sometimes there are barriers, and we are not really able to reproduce exactly the same scripts. So if we had a little bit of a layer of abstraction and a common language to run tests on a target and to collect the results and share them, maybe we can kind of forecast the cooperation and the exchange of information. And one of the last goals was, okay, once we have all these tests, everybody's developing its own tests. If they are all part of a common base of tests and is available to everybody, we can support kind of automated testing of kernel behavior and try to use that for regression testing. So this Linux Integrated System Analysis is an open source project, is hosted on GitHub, and fundamentally is an umbrella project that collects many other libraries that have been developed mostly within ARM, but not only. So there is a library, this deblib, that basically abstracts a target. A target can be either a Linux, a standard Linux machine, an Android machine, local also. It can be either remote or a local machine. The idea is that you have an handler at a certain point that you use to trigger commands on this target, whatever this target is. And if you use this handler, you can just change the target, the configuration in your test should run on each and every target. There are wrappers like on top of that. RTApp is a standard application. It's an open source project developed initially by this laboratory. And we have a wrapper on top of this library that allows to easily describe RTApp workflows, so synthetic workflows. And it's more easy to generate complex patterns, like, for example, we use for certain workload ramp tasks, so tasks that change their behavior a long time. Instead of writing a JSON file, which is required by RTApp by hand, we can have an API that allows to describe it. And being an API, you can easily change the parameter to generate different cases. We've integrated so traces collection and energy data collection with different energy models that are available as open source tools also. And at the end, the fundamental part where that I will talk a little bit more after is the part that translates the trace events into some kind of more consumable information and data structure. On top of which we can do plotting and analysis, statistical analysis, and so on. The final goal is to have this regression and regression analysis and scheduler behavior analysis. So one of the key concepts is this idea to start from an ftrace or a systrace, whatever trace file format we have got from the target, and using these libraries. Pandas is a standard library for analysis, data analysis, and statistical analysis of big data and data frame. So what we do is using a simple API call like that, the one there, we specify a set of trace events, and for every trace event, we generate basically a table. Okay, this table is a data frame, it's a Pandas data frame. And on top of this library, Pandas, there are a huge set of APIs to do statistical analysis and plotting and whatever you want to do. So the format that we use for all the analysis that we do is this format here, where basically for every trace event, provided that you generate trace events, also custom trace events, that they use this pattern, so they have a sequence of key equal value pairs. For every key, we generate a column, like here. For the com key, we generate the com column, and you have the value here inside. And once you have data frame, it's really easy to filter out events and look for whatever you want. There is a kind of a query language on top of this data frame. It's a really big API. So this API has been wrapped and make it easy to use using providing a set of predefined functionalities and analysis that we usually produce. And one of the things that we do is, okay, usually we want to share data with others, and we want a common representation in such a way that if I send a plot to someone of my colleagues, they know already how to read it, which kind of information are generated within a single plot. I'm just going fast across some of these plots just to give more or less an idea. So for example, for RTApp, and in the presentation are linked like examples that show how to generate these plots. RTApp is something that allows you to generate a synthetic workflow. So it's something that when a task runs, it runs for a certain period of time and then it stops, right? Depending on the frequency, so we configure this task to run for a certain amount of time given a certain frequency, which is usually the highest OPP of the most capable CPU in the system. But depending on the actual frequency when the task is running, this task can run for a shorter amount of time. Let's say that this is the time that we configure the app. If we are running on higher OPP, it will run faster, right? Because we are running on a higher OPP. If you are running on a lower OPP, it's probably running longer, right? And usually configure a period so we can measure different metrics. This is a definition of metrics, and Sana is another one that we want to introduce. But at the end, the point is that using this metric, we can figure out a performance index for this RTApp. You can see how many times this instance is breaking the period, so it's running longer than the expected period. So we can plot this period and see statistical distribution about how the RTApp is working. There is a plot, but there is also numerical data that are generated for every task. Another thing is, for example, we want to analyze scheduler signals. So this is a ramp task that is changing its behavior every 2 seconds. So every 2 seconds is increasing the utilization on the CPU. And this is basically the PEL signal, the utilization average generated by this task. You can easily see it And this is an example. We was developing a feature which was called boosting on top of the utilization value. And we want to verify that from this signal, we can generate another signal which has certain properties with respect to the original signal moving on. So we can graphically view it. We include other information, like, for example, this is the capacity of a little core and the capacity of a big core. So we can see when we are crossing threshold points, which kind of features are generated there. And we can see this vertical bar represent the system being overutilized, which is another concept in the scheduler. So we know that the scheduler behavior is different depending on whether we are in an overutilized region or not. So at the end, all this information plotted within a plot, they provide a more fast view and check of behaviors. That's a plot, and there are also numerical data that can be processed using scripting and whatever. Another example is CPU frequency. So we want to see how the frequency for two clusters are changed across time. And the important thing is that all these plots, the previous one, this one, the following, they are all synchronized. So if we zoom in a region, all the plots are scaled, and we have a consistent view across different metrics and different plots for this specific feature. And we generate, for example, the average frequency, which is computed out of a trace. So if you have a side-by-side comparison of two runs, you can see if the average frequency is higher or lower. So these kind of things, we found it useful, usually. We have plots, for example, for residency in OPPs. So we are running a task, and we want to see, this is a percentage representation. So the different OPP that have been used during the execution of a workload, how much time we spend in percentage or in absolute time within this OPP. Or in this case, we are breaking down, for example, this is the overall time we have been at the lowest OPP, but this portion, the red one, was the portion in time in which we was actually running something. The rest is idle time. So we was at this OPP, but idle, with the CPU idle, right? So this kind of breakdown and now this change between different runs is quite useful to evaluate features. The same for idle states. Absolute times or percentage representation of residencies of idle times. Functional profiling, we find it useful because, for example, we change enqueue task fair, we add some modification and want to see what is the impact of this modification on overhead. So there is a F-trace support for that, it's there, but it's easier if we can run with or without the patch and then just compare the two runs on different CPUs and see how much overhead we introduce, if we are improving the things or not. It's just a graphical representation, nothing more, but sometimes it's useful to share results. Couple more slides. This is, for example, latency analysis. So recently in F-trace has been introduced a new features that allows you to report what is the latency that the task has had. So the wake up latency or preemption latency, whatever. If you look at these patches, they're quite interesting, but it's quite a lot of C code to introduce this feature. So this kind of latency analysis was done way before in Python, as is like 100 lines of Python code on a trace which already has all the events that was there. So we are just using shell switch and shell wake up, processing this trace event after the trace has been collected, so not in kernel space. And we are figuring out more or less the same results. So we can see every time the application has been preempted, if it was a wake up, how much time he has spent before entering actually the CPU after the wake up, or if it has been preempted while it was running. We can set the thresholds and whatever, and this approach was quite usable to, for example, to verify that certain critical task in Android was not exceeding a certain threshold level in a big, in a long run. So with statistical data on top of that. Okay. Yeah, so that's more or less also all these plots. They are generated from data frames and statistics that we can generate also with numbers and whatever. The plots are just one kind of output. And I will hand over to Brandon that we show some real usage examples of how we use the API. Oh, there is any question on the first part, or we can pick after altogether? Okay.
I mean, we have loads of time to.
Yeah.
Any questions?
I have your answer. Just a quick question. As you allow to get all these metrics with this automation framework, I mean, you can plot them together. And is there anything, or are you thinking of doing anything outside of comparing automatically metrics? If let's say you have a couple of runs, you want just to find out, okay, there are 15 metrics that are all the same, but there is one that is going worse, that is particularly different. Do you have anything in there?
Yeah. So I would say that the general question is that it's all a set of features that it's in the list of things that we would like to do. We probably have something already because we are doing regression tests, so we can verify how a matrix is changing between different runs. But like writing a test that really say, okay, this is my reference, and then run it again and tell me which matrix is changing, whatever. These are things that can be probably easily added on top of the framework, but is not yet there. So we have what we have right now is, I think, is a pretty already usable API to introduce these features and introduce in such a way that they are then really available for everybody to use it. So it's important for us, I think, to collect feedback, what can be useful to us. And if this is something that we can describe, we can try to integrate.
Also, everybody is welcome to contribute to this thing. So since it's open source, I mean, we are, of course, more than willing to accept pages. And for us, it's really on development tools and stuff. So, yeah.
Thanks.
So I'm going to go into an example here. I'm going to go into some detail, a little bit of detail. We have quite a lot of time. So actually, I don't think Patrick mentioned that this all uses, although there is actually a command line interface as well. We mainly use the Jupyter or IPython interface, which is basically probably most of you guys have used it, but it's basically a interactive Python interpreter where you can execute a block of code and then you'll get the output, and then you can continue to execute within the same environment. You can go back and modify code and run it again, all with the same state. So I'm just going to run through an example. I'm going to try and be brave and run it live on my phone. So I'm connected to my phone via ADB, just a regular phone. Actually, it's rooted, but that's the only requirement that you have. And last time I did this, there was a thermal throttling which broke everything. So hopefully this time that won't happen. So just firstly, some boring setup, set Python environment up. So this is basically the configuration that you need when you connect to a target. So I'm saying it's an Android device. I'm saying the name of the device. So it's a Google Pixel, and that means that the Lisa has some built-in information about Pixel, which is basically just the CPU topology. So it knows the relative capacities of the CPUs, and everything else really it can figure out from the target. And I've got the ADB device ID. I'm configuring ftrace to say these are the names of the events that I want to collect, and I'm also enabling some inbuilt knowledge about CPU freak, not about this platform CPU freak, but generic CPU freak knowledge. So I'm going to connect. So then Patrick said that we had this wrapper for RTApp. This is an example of the API for that. So what I'm basically saying here is I want a ramp task that ranges over the course of so many seconds from using 10% of the biggest CPU's utilized capacity bandwidth, ramping up to 80% of that bandwidth and having a period of 20 milliseconds. And there's a few other of these similar classes. So there's one that's just like a static, provide me this much utilization for so many seconds, and there's one that alternates between two utilization values, and there's
you can compose them.
And then you can add them, you can concatenate them so that one gets executed followed by the other, or you can put them in parallel, that kind of thing. It's quite a convenient way to do it. And then there's a method to run that on the target that I connected to previously. So I'm going to do that now. And there's lots of output that you can see, but I've disabled it because it's boring and too noisy. And what I'm going to get back is that's going to collect the ftrace as well, and it's going to give me the path. So then I'm going to use the API, I think also Patrick had it, that parses a trace. I'm going to give it a little bit of platform data, which is basically, again, the relative capacities of the CPUs, which is really just so that we can add in some extra information in plots. So there were those horizontal bars on the scheduler signal plot. Those are showing, I guess they were kind of showing where you want, at what utilization value you would hope that task would migrate to. That kind of thing. So then this, this isn't actually part of any of the standard APIs. This is something that Trappy, which is the trace parsing library, provides, which is just a nice sort of JavaScript way of doing essentially the same thing as kernel sharp. So you can zoom in and you can see all the activations and where they happened, see the names of the tasks. So it doesn't do much more than that, but it's just a nice way of checking that roughly the behavior expected was seen. So I guess here you can see that over this side on the left, the activations are quite short, and then if I scroll along, they got a bit longer, and then we got probably the CPU frequency increased. So this is one of the canned plots that Patrick was talking about. So you basically have a set of pre-provided plots where you just throw a trace at it, and if you, for example, just want to see what the load tracking was doing while the task was running, this is kind of what that will look like. So there you can see it. That looks good. If the task was ramping up, you'd expect the util average to ramp up. That's the green line. And load average is only slightly above the util average, which I guess tells me that the task wasn't waiting on the run queue for much time. So that's helpful. And I can see the CPUs that the task was running on, so got migrated quite a lot. But there you go. And some more same. But this is where it gets interesting. If you're interested in this kind of thing, which we all are. So again, okay. Oh, do you know how to enable it? I disabled the logging. Okay, well, actually, Patrick showed that on his slide. He had the trace command output, which is the textual representation of the trace, and then there was a data frame showing the exact same data, and this is just another example of that. So this is the CPU frequency event. We've got these columns that start with double underscores. They're the ones that are implicit in the ftrace output. So you can see the CPU, you can see the PID that was running at the time, and these are the ones that are actually added as key value pairs in the text of the column. So then I'm just going to give you a couple of examples of why this pandas API is really nice for dealing with this data. So this CPU frequency data frame is kind of awkward because if you wanted to just get the frequency data for CPU 0, you would basically have to filter out all the rows where the CPU column has 0 in it, which is kind of awkward. So what we'd really like is to have, we'd like to drop the double underscore rows, columns, we don't need them, and we'd really prefer to have the CPU numbers being column headers. And there's that, basically that operation is provided by this pivot method, which you don't really have to think about too much. Then I've also just like extracted only the frequency data because I don't care about CPU, com, that kind of thing. And then I've added in, I've just filled in the rows with no data. So what I now have in one line of code is a table where the row indexes time and the column indexes the CPU, and the data is the frequency that CPU is running at any given time. Now, this is going to seem silly because there's actually a trace event called CPU capacity, but imagine there wasn't. And I happen to know that all the CPUs were the same architecture, so that the frequency related directly to performance or CPU bandwidth anyway. With a fairly simple single line of code, I can convert that frequency data to relative capacity data in the range of 0, 1, 2, 1, or 2, 4. So it's kind of, you want your util average for the root CFS run queue to be less than this value. Yeah. And this is, so I've taken a bit of a long way around on the previous example. So this is basically does all that in one go for a different event, but I didn't want to just jump over it. I wanted to show you the flexibility of the API. And now I have, so what this is giving me is the util average value for the root CFS run queue for each CPU. Let's have a look at the data. Looks like that. That's not interesting. So, yeah. And then I can, using the plotting API that's provided, so I'm looking at CPU 1 there. we run on 2 and 3. Looking at CPU 2, I can see that it was pegged at the highest frequency, interestingly enough. So what I was hoping to show you was that the blue line would show the utilization of the CPU, and the green line would show the CPU freak governor just sort of skirting over that util average value. But for some reason, it was pegged at the highest frequency. Is that right? Yeah, it was. Okay, so I don't know where that was, but so I've identified a problem with my kernel, which is, and it was all I had to do was a few lines of simple Python. So that's the first example. Any questions?
So the data that this is working on are the data that were collected using the Panda library that was shown by Patrick.
Exactly, yeah. So well, the data was actually collected using devlib, yeah, and then parsed into a pandas format. So actually, devlib collects the data, a library called trappy parses the data, and then provides it in the format of the pandas object. And pandas gives you all the manipulation and plotting.
You can collect the f-trace wherever you want. If you have an f-trace output, you can just start from that point, yeah, and translate the f-trace into the data frame format. And then the APIs work on that format.
So actually, Patrick from Baylibra was saying yesterday that there's quite a lot of components here, but if you're just interested in parsing and analyzing traces, you only really need trappy. And so then you can collect an f-trace by your own whatever, and then you can use all of these APIs for trace analysis and plotting or with just the trappy library. And what else? There's another thing that trappy does that I haven't mentioned.
Plotting,
that's
comparison. There is an API to compare to different runs.
Oh yeah, yeah.
So if you have 2 runs, you can compare 2 traces, like plot 2 signals. Let's say that you collected 2 traces, and you can plot the 2 signals on the same plot and see how they differ between the 2 traces. That's another feature of this plotting library. Yeah.
So let's do another example. Should I do the IRQ?
Yeah, that can be interesting for
periodicity. Yeah. So at Naro Connect, Daniel did a talk about new
IRQ prediction.
Yeah, IRQ prediction by analyzing the periodicity of interrupts.
Yeah. So all these API now they are used within this notebook, but at the end it's just Python code. So provided that someone accepts to use Python, you can just write your own script in a file, and the same things works. You don't really need to use this environment. We find it usable because it kind of mix code with results. You can add text, comments, and whatever you want, and then at the end you just export the HTML file, you send it, and you have everything there. So the script to run the whatever test, the results, the comments, and everything is packaged together. But yeah, at the end, it's just Python code. So it can be a standalone script.
Yeah. So I'm just going to whiz through the beginning, basically the same setup as last time. This is using a different API. It's more abstracted and generic and shorthand, but it's not really worth talking about right now.
That would be my question. What's the learning curve of your tool? How it's easy to use that from scratch?
So what that's the big point for that. So what we have done is we provide on the website. There are a set of notebooks that is a kind of tutorial that works through the different APIs and provide a simple example of it. So I think it's like 10 different notebooks that works through the API, and it can take probably 1 day to go through all of them, and then it's a matter of using the things. And most of the time, we ourselves also do copy and paste. We have a note to know that this is the code that I need. I just copy and paste this API and use it. Apart from the time when we want to develop something new. Yeah. But yeah, the learning curve is something that is also kind of it's difficult to. It's the main difficulties. I think it's approaching the idea that it's Python, so which is maybe something that someone is not used to using. But the simplest API, it's most of the time just copy and paste 10 lines on Python from an example, and you get some plots that are still meaningful.
Yeah.
So I guess one of the things that can confuse people is that there's quite often two places where you can, there's sort of this stack of abstractions and you can enter it up here, like I've done here. And that's typically, so you look at that and it probably makes no sense. Whereas in my other example, I entered it at the lower level of abstraction and it was much simpler to understand.
That's my point. I mean, look fine, but how to have a view of all the interface and which line I should use?
So the difficulty stands in the fact that you can call it a tool, but it's not like a graphical tool or whatever that you have to. It's an API. So at the end, it's just kind of learning step by step the piece of API that you need. And it really depends what you need and how much time you spend on it. But at the same time, it's flexible because being an API, you can customize it to whatever you want.
So when you install it, you get a load of tutorial notebooks with some text and examples, and then there's also some example notebooks, which just, I guess they're really designed for the copy pasting thing. So that
so what we are starting to do, if you go in the examples, like energy meter, for example. So every time we integrate a new API, we try to put now a simple notebooks that, for example, show you how to use this specific energy meter. And there is an example that shows you how to run a workload and collect energy samples from these things. And this is the minimum notebook that generate a workload, run it, collect traces. So we started recently to do this kind of notebooks, but the idea is to keep going on that way. So for every new bit of API, there will be a small notebook that show how to use it. And for every release, we basically add a notebook that points to these. Okay, these are the new API added, and these are the notebooks that show you how to use it.
There's API documentation, but it isn't hosted yet, the HTML. So something probably in the next 10 days or so, that'll be on Read the Docs.
I know when we first started to use it, we had a lot of trouble. So now you've got pixel support and everything, but at the time, it didn't know how to parse the output of RF trace, I guess.
systrace.
Right, the systrace outputs and stuff. And so it seems like if what you're trying to do is already in the library, you can enter this high level of abstraction. In practice, how many people can actually enter at that high level of abstraction? How many devices do you have?
So, this issue was more an issue of format representation because Android doesn't use ftrace, it uses this systrace, which is embedded or whatever. So it was was missing a bit to parse the data. But then the API was there, and there is all the difficulties that we described before. You have to kind of learn the API, right? If you have a new device, usually the trace format is always ftrace for most of the cases, apart from Android. We use ftrace also for Android.
I mean, Android using ftrace too. It's just that initially it was slightly different.
But there are no other specific platform dependencies in the API. It's not really there. I mean, the only bits.
Well, I mean, that certainly could be when you're driving tests. ADB, there's ports of different devices.
But this is pretty. I mean, we can connect ADB targets, SSH targets, and we can run on localhost, and this is covering more or less everything. From another perspective, I mean, we are more than willing, if the tool is considered to be useful, to collect feedbacks from, I would like this feature, and please add it, whatever, and try to put a reasonable bandwidth.
Anyway, it seems like it's getting a lot better. Our experience certainly was that the barrier to entry was very high. And but it is getting lower, and the more we have sort of canned notebooks that somebody says, I just want the frequency distribution during this run. You've got that. So, so it's getting better.
As for quirks, the devlib, which is the library that handles target connections, that actually knows about a lot of quirks with things like ADB. So like some devices report the error code when the target command fails, and some of them don't. And so it knows about that kind of thing, and homogenizes those behaviors.
Right. Well, it knows about those things for those devices that you have.
No. I mean, no. You don't have to tell it. So like for example, when I was using Pixel and then I upgraded my Android SDK and ADB's behavior changed, Devlib knew how to deal with that. I didn't have to say I upgraded my SDK or I switched to an Android N. So, but of course, when a new quirk comes up, you have to submit a patch to support that quirk. So, Yeah, I'm just going to whiz through the example that I did at Budapest. I've run that, it looks like. So I've run, what have I run? Oh, I haven't run anything. That's right. So I'm about to run is just a single 20% task that lasts 2 seconds with a 10% period. I'm going to plot the behavior so you can see there's some noise on these CPUs, there's some noise on this CPU, and there's my workload pegged at a low frequency. So yeah, something wrong with my kernel. Shouldn't be pegging the CPU. And so what I'm basically going to do is get this trace back and look at the IRQ handler entry event. And I'm going to use this pandas API. And what I'm going to do is I've defined a function which I can pass in a subset of a data frame, and it's going to find the difference between each successive event in time. Then it's going to create a new data frame showing, with one column showing the delta in time between each successive event, a pair of events, and the time at which the second event occurs. So what you basically have is a data frame where an entry for a given time shows the time since the last entry. So every time you enter an IRQ, you know how long it was since you last entered an IRQ. So first of all, I'm going to, and then it's going to plot essentially that data on a graph like this. So this x-axis shows time, and the y-axis shows the time since the last event. So each of these dots is an interrupt, and the higher up that interrupt is, the longer it was since the previous interrupt. So if I just plot all the interrupts, it's going to be really noisy and useless. And I've got a histogram here of the same data. But then using this API, I can easily filter it so that I can just see interrupts on CPU 1. That's not very interesting. Let's look at, CPU 1 was idle mostly, wasn't it? So let's look at CPU 2.
Can you make that per CPU? I mean, for that, it's your tracing all interruption. Can you filter and give the same per CPU on the CPU?
So do you mean
per IRQ? Sorry, on one CPU, can you create such kind of graph per IRQ?
Yeah, I think that's probably what the next line does. Okay. Yeah. So this is the list of all the names of the IRQs that we found. Okay, no. So this is just plotting the arch timer IRQs, and I could probably do something like IRQ name is arch timer, and IRQ CPU.
So that's interesting to show the workflow that we usually use. So we play a little bit in interactive way like that, and then when we find, okay, I would like this kind of plot where for every CPU I have this plot, then at this point we introduce a new kernel plot that is parameterized in such a way that we can easily ask, okay, plot me these IRQ on these CPUs. Okay. And it's just a method to identify use cases, play a little bit, find it, and then generate a new API that produce whatever we want, and then we start using this from this time on.
Yeah. So I guess, let's see, we can find an example of where it was nice and periodic.
You can take the EWC3, because this is the timer that you are using.
Yeah. I was thinking that the time would be the most periodic one. What else have we got in there that looks periodic?
And CPU 0 maybe.
Ooh.
Only CPU 0. Move on the CPU 0 to get some value.
We didn't have that many interrupts there. But so, yeah. Okay, negative result. None of the interrupts were very periodic because none of these histograms have a big peak. Although there's something somewhere that's very periodic. There's a peak here. So, yeah. I guess I'll go through one more example. I'll go through the automated tests.
Yeah, just one simple example of the test, because well, this is the interactive way we use it. And this API then they are used, we are writing a set of behavioral tests that verify specific scheduler behavior. And maybe you can go through the, like the capacity frequency variance or capacity variance, just to show briefly how it works.
Yeah, so I guess,
so we have a collection of tests specifically for ES that we run periodically internally to do regression testing.
So yeah, basically using all the same APIs, you can make assertions, which is nice. So what this test does, I'm not going to go through it because it's quite a lot of code, but it's basically going to read the target using Devler's API, which knows about CPU freak, so it's going to figure out all the available CPU frequencies. Then it's going to run an RT app workload at every frequency available, or actually just a cross-section of frequencies because there's loads on this. So it just runs, I think, 8 frequencies across the available scale. And then it's going to use the trace points that we've added to the kernel to extract the scheduler load tracking signals. Actually, DeepMind submitted a patch to LKML, right?
Yeah.
For
trace points.
Trace points for load tracking signals. Yes. So a much older iteration of those patches for, what do they call them at LKML, the upstream? Shed load average. And then it can make assertions. So I can basically, this is CI friendly. The point I'm trying to get to is that I don't need to be sat there with babysitting it. I can just run this on a Lava farm or something else, and it'll tell me if my load tracking is broken for frequency invariance, which it is. Oh yeah, because my phone is thermally throttled for some reason.
Yeah. So we calibrate the RT app every time we run a test.
Well, and if it's pegged at the highest frequency, it's no longer it's throttling.
Yeah. Yeah. So what's happening here is the reason it's complaining is because I've told it that I'm running a pixel. It knows that CPUs 2 and 3 should have higher bandwidth than CPUs 0 and 1, and it's finding that that isn't the case. So it's complaining because all of my assumptions are wrong. So yeah.
But otherwise, we check the data frame and verify the capacity is properly scaled.
I actually ran it earlier. This is what the output looks like. Yeah. So I guess that's probably all the examples that this was going through. Is probably enough detail. But
any more was to give more or less an overview of the tool, and somehow, just ask for feedbacks in general, if it can be useful or not, how it should be extended, maybe these kind of things, and I mean, the call for cooperation is at least on giving input on what should be nice to have. Or otherwise, if there are opinions that, okay, it's not really useful, it should be useful a different approach or whatever, that's also not a problem.
So how many custom trace events do I need to actually use all the features of this?
So yeah, that's a good question. So right now, so for most of the scheduler bits, there are not really trace events for scheduler signals, apart from the trace point that DeepMind is trying to ask for review. So we have a set of trace points, which is like 7 or 8, I think, something like that, that we kind of maintain for specific kernel version. We try to keep them aligned on DeepShed core or for specific Android versions. And we link from Lisa a Git repository that lists the 8 trace points that we use mainly for Android. But yeah, we need this as well. There are many APIs like like the plots for things that they just use standard events, so CPU frequency, CPU idle, whatever. So they are already there and they can be used. So frequency, residency, idle state residency is supported by standard trace points.
So I'm going to go Greg's get switch trace point.
Shed switch is it's used quite a lot.
Yeah, so we want to change that.
Yeah.
Will you then be unhappy or just change it?
No, so our commitment is, of course, the idea that the API has to be aligned. Actually, what we do, because we have different trace points, for example, in Android, we change it in different versions. There are different signatures. Within the library, what we are doing is try to, we usually are able up to now to identify what is the format, and we always convert to a kind of common format which is used by the plots. So the plots are always working independent from the original trace point. If some information are not available in the new trace points, maybe there are features that cannot be used because we don't have this information. But whatever is there, maybe with a different name or form or whatever, it's available. provided that we have these syntax which keep equal value, which however is generated by.
Well, and actually, even that constraint isn't universal because shed switch already doesn't follow that format.
Yeah, no, there is that's why we dump the raw format of F3. So there is a dump raw format that always generate equal value pair. That's why we use it. And then you can add whatever custom events you want. So we usually also add or inject trace point from user space, and we always format with this format, and then we can parse them and we can generate data frame. You can just look. You just have to put a key, an attention word at the beginning, which is something column, like shed which column. Okay, it's my event column, and then this is parsed by the trace parse, and they generate a data frame. It's there and you can use to do whatever you want.
We very often break backwards compatibility in the trace points that we add. I know that's easy for us because we also are experts in the tools that parse it, but it's very simple to update the tools, and it's much easier to update the tools than it is to fiddle with the kernel to make the trace points backwards compatible.
Yeah. So that's my hatred of trace points, is that people start to rely on them and they become API.
No, that's not our constraints. I mean, we are more than happy to be as much as possible backward compatible and just figure out the runtime.
So in which way is it going to change?
We're not quite sure yet. So we need to add support for scan deadline in a whole bunch of trace points. People don't like the idea of always dumping out all the information. They feel that the trace point will become too big. But then you get into the area of dynamic trace points, and then you need to somehow communicate to user space that there might be different formats for the one trace point. And we're discussing on how to go about that. The current proposal is to have a whole bunch of trace points all named similarly. But that is ugly. And it is inconsistent in the interface because, so for example, you have scat switch spare, scat switch RT, scat switch deadline. But only the enable bit of the scat switch one actually does something, and the other ones are there just to represent the format of the trace point that can happen if you enable it. So that's we're discussing, and that Daniel works.
Yeah.
So yeah, he's been working on that, and it's scat switch, and it's a few of the other ones. It's the priority inheritance one. It's I don't know. So yeah, we're struggling with that. We know we want to break it. We're not quite sure where we want it to be. We're trying to convince Steve to allow us to change the format file to list multiple formats in one file, and then keep the one name representing the one trace point idea. So yeah, we'll see.
Okay.
The problem now is a trade-off of putting a lot of data in a single trace point, or trying to make a lot of trace points to reduce the size of the data for each trace.
Which we want to, but then we get into trace API issues, and so yeah, we're struggling there to convince everybody to agree. And
so the issue is risking to break now user-space tools that rely on the current format.
yes,
Okay.
so there's a whole bunch of tools, including Perf, which has snake bits in and God knows what, that rely on the current format of ftrace.
Yeah.
And rely on. And there's even more tools that rely on the ftrace API as it exists, and we want to break everything.
Yeah. So we're getting to the point where you need a version for each trace event, so you can actually see from the trace.
This has been suggested that people hate that, and so yeah, there's a lot of unhappy, but we need to find something. Yeah.
Steven mentioned increasing he mentioned transforming the trace CMP on the library and access everything through this library.
So no, I don't. So I'm the idiot that uses the debugging interface, uses the raw trace ASCII output and applies awk, and then does the plots in his head. I don't use any of this. So if there was only binary data, I'd be screwed. So then I'd have to learn how a tool works, and I'm not smart enough for that. No.
Sure. That's another question.
So do you have any plan to extend or to monitor more events than the scheduler?
So you mean like user space?
Not really user space, but maybe more IOs or peripherals. Because
Okay.
So you
Well,
have processes that are IO dependent. And to know more about the platform, the scheduler may be not enough and may not provide all the information you may need. So knowing more about what's happening in the form.
But the trace format that we use is ftrace. So every trace point is available or generated in kernel space can be consumed by the frame. So
Yeah, we also already support thermal, for example.
thermal, yeah, but via trace points.
Yeah.
Yeah. So yeah, if subsystems want to use the tools, it's just the method to generate a sensible trace event somewhere with the data that you want to parse, and then it's there. If I got corrected the question. Another perspective is trying to mix user space information with kernel. So what Android does is just injecting the events in the ftrace, and they are there, and so you can consume that, parse them, and consume that.
About that, to your knowledge, the DMA subsystem use the trace.
Well, it's not in my knowledge. I guess maybe
I
there are
asked
some.
because,
Yeah.
can be useful to trace DMA events about the peripheral interface.
Yeah, I guess it's something maybe DMA really platform dependent, and so I don't know if there are, because ftrace is a collection of more generic class of events, so probably it's not there. But still, I mean, if you have your own driver or core or whatever, just put a trace point, whatever. We use a lot of custom trace point.
I'm not sure, is there any runtime PM trace events? Oh, probably. So you can track device activity with that. So at least some level of activity.
Yeah.
If there's no event using the proper events API, you can also just do a trace print K. And if you make your trace print K look like a row in a trace command report, then it will turn up in the trace print.
Yeah, by the way, a question about this one. We always said that. So if we use a trace print K, it's not an higher overhead than using a standard trace point. I mean, it's the data injected in the trace is still a binary set of data that we format with the trace print K format string and a format string. Or it's better to always have like trace points, proper trace points.
Proper trace points are better. I forgot what all trace print K does. So I don't think trace print K has the jump label.
No, it doesn't.
And
No, it doesn't. It goes unconditionally.
right.
Okay.
So,
Yeah, but usually if you have a
for
trace print K,
debugging, it's fine.
Yeah.
It's
Yeah.
just for really don't want it in a production kernel. That's why
Yeah,
they
sure.
have
Yeah,
it from-
it's
Yeah.
a message at the boot.
yeah, because you cannot really disable it, so it's always there. And yeah, but usually we do that. I mean, if there is a specific feature that we want to debug or analyze, and there is not a trace, one can just put a trace link. It's really simple.
Yeah,
Just
everybody
format
does that.
and you get whatever information you want.
And don't ever send patches with trace print K. Then you'll get wet on the head. But other than that, you have
Yeah. Okay, I think we are over there.
Thanks.